Today, we want to talk about the relationship between the derivative of a function and the graph of a function. We know that the derivative of a function tells us the slope of the line tangent to the curve at a given point. That's the origin story of the derivative. That's where we started thinking about this derivative. That's where the derivative came from. We know that the slope of a line is the rate of change of the line, and the tangent part is us calculating an instantaneous rate of change. That's where we go from an average rate of change over some finite change in y divided by finite change in x and just having a nice division problem to an instantaneous rate of change when we're essentially calculating 0 over 0 because we're doing a tangent line. We're calculating a slope at one point. So we had to build a lot of machinery to figure out what 0 over 0 was in these particular cases. So here's what we want to, where we want to go with this. If the slope of the line tangent to a curve at a given point is positive, that means that the function is, the values of the function are going up. The derivative is pointing us in the direction of the function. The derivative is telling us the direction of the function. Specifically, let's just say it. Just say it. The sign of the derivative tells us the direction of the function. The sign of the derivative tells us the direction of the function. Let's suppose this is what our function looks like. We can see this little peak, and then there's a peak, and then up here, there's a valley down here. So if I mark these two peaks off, let's say I'm going to call this x1. And this point will be x2. At x1 and x2, if we calculate the slope of the tangent line, we'll see we have a horizontal tangent line. So the slope is going to be 0. So f, the function, has horizontal tangent lines at x1 and x2. The function has horizontal tangent lines at x1 and x2. That's a little bit shortened. I probably should say the graph of f has horizontal tangent lines at x1 and x2. But since I'm talking about a graphical feature, when I say f, I mean the graph of f. These are the 2 points where the derivative is equal to 0. The slope of a horizontal line is equal to 0. So these are 2 points where the derivative is equal to 0. So what this tells us is that the first derivative evaluated at x1 and x2 should equal 0. Slope is just first derivative. And if I evaluate the first derivative at x1, we'll get 0. And the first derivative evaluated at x2 is equal to 0, because slope is derivative. We can describe the behavior of the function in between these points and outside of these points. We see that before x1, we would say that the function is increasing. The values of the function are getting larger. So for x less than x1, we would say that the function is increasing. The function is increasing for x less than x1. It's neither increasing nor decreasing when x equals x1. So it's increasing for x strictly less than x1. After x2, the function is increasing again. So f is increasing for x greater than, x less than x1 and x greater than x2. If we think about a tangent line before x1 or after x2, the slope of the tangent line will be positive because we'll be going up from left to right. So if I draw a tangent line at some point before x1 or some point after x2, I drew a little bit flat. What we notice is that the slope is positive. The slope of the tangent line is positive. The slope of the tangent line is positive for x less than x1, before x1, and after x2. Here are other ways I might say that. Before x1 or after x2, in just like speaking language. So the slope of the tangent line is positive before x1 and after x2. So we would say that the derivative is positive before x1 and after x2. We can see that the slope of the tangent lines is going to have a delta y over delta x. Delta y is going up when x is going up, and that's going to be positive. Positive over positive is positive. If we go back the other way, then delta y is negative, but delta x is also negative, and we get a positive slope. In between x1 and x2, I'm going to say the opposite. So multiply by -1. So between x1 and x2, we would say that f is decreasing. The function is decreasing for x between x1 and x2. x1 less than x less than x2. This is us saying x1 is between x1, x is between x1 and x2. We would say x between x1 and x2, we would write x between x1 and x2. If we look at the line, slope of the line tangent to the curve in between x1 and x2, we will see that the slope is going to be negative. The tangent line is headed down. The slope of the tangent line is negative, and because this is calculus class, when we say slope of the tangent line, we mean derivative. So the derivative will be negative between x1 and x2. Note that in this case, I'm saying strictly less than instead of less than or equal to, because the function is not decreasing at x1. So I don't want to include x1 in my inequality. So when we put an extra line under the less than, when we put an underline on our less than, we're saying less than or equal to, and it means a different thing. So x less than x1 means x is not x1. So strictly less than means x1 is not, x cannot be x1. X less than or equal to x1 means x1, x can equal x1. That's the or equal to part. Questions? The sign of the derivative tells you the direction of the function, tells you the sign of the derivative. When the derivative is positive, the function is increasing. When the derivative is zero, the function is flat. When the derivative is negative, the function is decreasing. Sign of the derivative tells you the direction of the function. Sign of the derivative tells us the direction of the function. And this works both ways. If we see that the function is increasing, we'll see that the derivative is positive. If we see that the function is flat, that will happen because the derivative is equal to zero. And if we see that the function is decreasing, that will mean that the first derivative is negative. These are the three things that could happen with a number. It could be zero, it could be positive, it could be negative. If the first derivative is positive, the function is increasing. If the first derivative is zero, then the function is flat. If the first derivative is negative, then the function is decreasing. Another thing that we want to notice here, I just started calling the derivative the first derivative, implying the existence of a second derivative, and a third derivative, and a fourth derivative. And eventually we'll start referring to the function as the zeroth derivative, although that will sound really weird. So we're going to start referring to f prime as first derivative. If the first derivative is positive, the function is increasing. If the first derivative is zero, then the function is flat. If the first derivative is negative, then the function is decreasing. Questions? Comments? Side remark? Is everybody okay? Everybody looking at me suspicious. I don't know, probably on me, but everybody's looking at me, and I think it's the way you always look at me, which is kind of like, but today it feels suspicious, and I don't know why that is. Because I'm not allowed to read your minds. Normally, in the past, I would just be like, oh, are they being suspicious of me? And I was just like, read their mind, read your mind. Like, oh, you can't read minds anymore. I'm like, oh, yes, I can. It's like, oh, you're not supposed to read minds. Like, see, that's different. You know, like, I'll lead you a pain in the ass to talk to. Like, oh, well, yeah, that's by design. It's to try to keep you talking to me all the time. And they're like, oh, if you don't like talking to people all the time, why did you take a job where your job is literally to talk to people all the fucking time? I'll quiet you. I've heard like the number one fear. Does anybody know what the number one fear is that most people have? Like if you had to people had to list off fears, what's people's like number one fear? It might have been changed, but like classically, what's the number one fear that people have? Public speaking, right? And you were like reluctant to say it because like, well, because the number one fear is public speaking. Is like, it's like why teachers, when teachers get like, so my students, I have to call on my students, they don't volunteer. It's like, well, do you know what the number one fear is? It's like, and you're asking them to do it. Like some of you are like, well, I don't care. It's like, well, then it's not your fear, right? Some of you don't care if there's a spider in the bathroom or something like that. You just like scoop it up on a piece of paper. It's like, well, dude, we're going outside. And your spider's like, well, there's bugs on the inside. I'm just going to come back in to eat those bugs. Don't kill the spiders, what I'm saying. They're eating the other bugs. They're useful. If they're like on the floor, they're like, oh, I'm not supposed to be here on the floor. I should be up where the flies are, then like put them back up on the ceiling. You know what I mean? Anyway, beside the point. Because I don't like, and I'm like, oh yeah, I agree, because I don't like public speaking. And people are like, oh dude, isn't your job public speaking? It's like, oh no, absolutely not. I mean, y'all are the public, but y'all aren't the public. You're what we like to refer to in the business as a captive audience. You're fucking stuck here. And when I go off the rails like I am right now, it's like, you can't just like get up and walk out, right? Like if this was like a show or something like that, and you're like here and you've reached your 2-drink minimum, you just get the fuck up and walk out. Well, this is not what I signed up for, and you just leave, but you're like stuck here. So this is not public speaking. Public speaking, the fear is that you will visually see people disapprove of your speech and then get up and walk out, right? But here, you all feel obligated to like stay, even though you are actually free to get up and leave at any time. Some of you have discovered this. Sometimes like scheduling means that you have to leave this class early on certain days. And you actually ask me if that's okay. And like, what am I gonna do? Stop you? Like if you like start packing your stuff up, if you do it quietly, like, do you like start packing your stuff up and start heading for the door? I'd be like, oh, we got a runner. And like security is like all running after you. With open hands like this, like Tom Cruise style. Because he's a robot. I don't know if you knew that, but that's beside the point. This is the thing that we want to take today. All these words to get down to this little box. If the function is increasing, the first derivative is positive. If the function is flat, then the first derivative is 0. If the function is decreasing, then the first derivative is negative. That goes both ways. So that's an if and only if statement. So if the function is decreasing, first derivative is negative. First derivative is negative. If that's what we find out first, then we know that the function is decreasing. Always they go together. This arrow that goes with both ways, this two-headed arrow, that's an if and only if arrow. One of the things I said before, I was like, I'm just going to say the obvious things. Things that are obvious to me are not obvious to everybody. As humans, we come programmed with exactly one app. When we're babies, the rest of it has to be loaded on. And if you haven't seen something, then it'd be unreasonable for me to expect you to know it. Do you know what I mean? So this is an if and only if arrow. A, if and only if B means if A, then B, and if B, then A. They go together. So when you see that double-headed arrow between two statements, you could read it as if and only if. It's a little more complicated with the if A then B, because you might have said A out loud and you're like, oh shit, I didn't say if. So at that point, you could just say implies. So you might read this as A implies B. Any questions? Comment? Any thoughts? When the first derivative, the sign of the first derivative tells you the direction of the function. The sign of the derivative tells you the direction of the function. Positive first derivative, function increasing. 0 first derivative, function flat. Negative first derivative, function decreasing. I know I keep saying the same thing, but songs don't get stuck in your head because you hear them once. I know I keep saying it a little bit different every time, so I guess it's like postmodern jukebox remix type of stuff. Any questions? Comments? Any thoughts? Snide remarks? Happy thoughts? F has a local maximum at C if F changes from increasing to decreasing at C. F changes from increasing to decreasing. We say local maximum because it's the highest, it's a peak, but it's not necessarily the highest peak on the entire graph. This classroom is a local maximum. It's the highest classroom that we have, say, on the campus. It is not, however, the highest classroom that we have, say, in California, because there's a school in Lake Tahoe, and that is at a higher elevation. This is a local maximum, not a global maximum. So local versus global. So F is changing from increasing to decreasing at C. What that means is for the derivative is that the derivative will be changing from positive to negative. When a function is increasing, the first derivative is positive. When a function is decreasing, the first derivative is negative. So when a function changes from increasing to decreasing, the derivative is changing from positive to negative. If the first derivative is changing from positive to negative at C, that means the first derivative is probably zero at C. Not necessarily zero at C, but probably zero at C. It might be that the function is flat. Remember, first derivative positive, first derivative zero, function flat. Yes. Yeah, we read from left to right. We always think of X X going in one direction, X going in the positive direction. We can do a similar thing with local minimum. When I say we could do a similar thing, that means I don't want to write it. Trade minimum, what would I trade? Well, how would I rewrite this? If F has a local maximum at C, if F changes from increasing to decreasing at C, that is F prime changes from positive to negative at C. If I trade maximum for minimum, what do we have to do? Flip those two around. F has a local minimum at C if F changes from decreasing to increasing at C, that is F prime changes from negative to positive at C. And that still means that F prime of C is probably zero because the function is probably flat. So this raises a question. What do you mean probably? How can we go from a positive to negative without being zero? How do we go from increasing to decreasing without being flat? This is a great question. I'd be happy to tell you. Furthermore, if I tell you this right now, then it'll make a lot of calculus make a lot more sense for the rest of the semester. And your mathematical life will be easier from here on out. But only if I tell you right now. If I wait like one day to tell you what I mean by probably, then it's kind of ruined the instantaneous effect. And instead of just downloading stuff in the Matrix, a very old movie that some of you probably haven't even seen, and working through thousands and thousands of problems and thinking about stuff, doing hard work, is the difference between telling you now and telling you anytime after now. So I have to tell you right now. So let me tell you what I mean by probably, so that calculus will be easy for you for the rest of your life. So here's the secrets, the great secrets to the universe. Oh, darn, look at the time. That's going to do it for today. I will see you all on tomorrow. And I guess we're just going to have to work through this at the normal rate. Bummer. That's it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.